Welcome back. So in today's lecture we are going to discuss on strengthening mechanism, which is very important topic in mechanical behavior of materials. So before going to the types of different types of strengthening mechanisms, we should know about the plastic deformation of a polycrystalline materials. So ordinarily ductility is sacrificed when an alloy is strengthened. Already I have told this in the very first lecture. Okay, so the ductility and strength both are controversial properties. If the ductility is increased, the strength will get decreased. If the strength is decreased, then the strength is increased, the ductility will decrease. Okay, so the relationship between the dislocation motion and the mechanical behavior of metals is significant for the understanding of these kind of strengthening mechanisms. So the ability of the metal to plastically deform depends on the ability of the dislocation to move. Okay, so if the dislocation is not moving, then there will be no plastic deformation in the metal. Okay, if the plastic deformation takes place, then the material is called as ductile. Okay, so that is, whenever we are producing a material, the material should be strong and ductile. When it is ductile, it can be changed into various shapes according to our needs. Okay, if it is strong enough, it can able to withstand the load. Okay, so the strength and ductility, both properties are very important, which cannot be compromised. So nowadays research work is going on in improving the strength of the material. At the same time, the ductility of the material is not getting sacrificed, okay, due to the processing methods. So virtually all strengthening techniques rely on the simple principle, that is restricting or hindering the dislocation motion renders a material harder and stronger. Okay, this dislocation motion, if we are restricting, okay, if the motion plastic deformation, if the dislocation is moving, then there is a plastic deformation. Okay, so if the plastic deformation is moving continuously without any hindrance, okay, the material will starts to deform plastically. Okay, that means the strength is getting reduced. Okay, now how to increase the strength? By bringing a hindrance to the motion of the dislocation. Okay, so restricting or hindering dislocation motion renders a material harder and stronger. Okay, so with this principle, okay, there are many strengthening mechanisms. Okay, one is called as a solid solution alloying, second one is strain hardening, third one is strain aging, fourth one is grain size reduction, and fifth one is precipitation hardening or dispersion strengthening, and sixth one is dispersion strengthening to reinforcement or composite, and seventh one is a martensitic strengthening. These are the common strengthening mechanisms available. We will see one by one in detail. So first one is solid solution strengthening. Already I have told you what is a solute, what is a solvent. Okay, a solute is the major some minor portion of the metal, and solvent is the major portion. Solvent is the major portion. Like that, if you are mixing two elements, okay, copper, nickel, okay, copper and nickel, okay, if the copper is more, then it is called as a solvent. Nickel is small, it is a solute. Okay, so both atoms, so both the atoms will mix together. Okay, so carbon will mix in, copper will mix in nickel, and nickel dissolve in nickel, and nickel will dissolve some amount of copper, okay, based on their solubility limit. Okay, so based on this, a solid solution will be formed. A solid solution is nothing but a solution, okay, which consists of a solute and the solvent. Okay, the solid solution can be classified into substitutional solid solution and interstitial solid solution. What is a substitutional solid solution? Substitutional solid solution is a solution in which in which the atoms are almost of the same size, that is solute atoms, solvent atoms are almost on the same size. Okay, already I told you about the Hume-Rothery rules when I am discussing on the previous lectures. Hume-Rothery is nothing but Hume-Rothery is a scientist who developed some rules for formation of the substitutional solid solution. All metals cannot form a substitutional solid solution. Few metals like iron, carbon will form a interstitial solid solution, because the atoms of iron are larger in size, whereas the carbon atoms are smaller in size, which is considered as an impurity which cannot occupy the same position in the lattice structure. Okay, so substitutional solid solution can be formed by these four rules. One is same crystal size factor. Suppose the solute atom and the solvent atom both are having a BCC structure, then there is a possibility of formation of the substitutional solid solution. Okay, so this is the same crystal size factor. Second one is relative size factor. Okay, the size of the solute atom and the solvent atom should not be greater than or less plus or minus 15%. That is, if the solute atom is 100, then solvent atom may be 85 or 115. Okay, like this the size should be there. Okay, it should not go beyond plus or minus 15%. Okay, so this is the second condition. Third condition for as per Hume-Rothery rules is the both solute atom and solvent atom should have the same chemical valence factor. Okay, relative valence factor, not chemical valence factor, relative valence factor. The valences of both atoms should be almost same. Okay, then only there is a formation of the possibility of formation of the substitutional solid solution. And the fourth category is chemical affinity factor. These atoms, okay, that is the solute atom and the solvent atom should not react with each other and they should not form a new compound. Okay, so if these four cases conditions are satisfied as per Hume-Rothery, then a substitutional solid solution will be formed. Okay, right. Now with this information we will go into strengthening mechanism by solid solution. So impurity atoms distort the lattice and generate the lattice strains. Already I told you when we are discussing on dislocation. Okay, if the atoms, okay, if this substituted atoms is smaller in size, that is I told you, no, solute atom and solvent atom size should not be greater or lesser than plus or minus 15%. That is, if a solute atom is 100, solvent atom should be solvent atom is 100, solute atom should be 85 or 105. Okay, so consider 85%. Okay, 85%. So it is a smaller in size. Then in that case you can see a pincushion distortion. Okay, so the edge dislocation is towards the center. Okay, whereas if the larger substitutional impurity, then you can see the dislocation moment is bulged. Okay, that is barrel distortion. Okay, so smaller substitutional impurity generates local stresses at A and B, then opposes dislocation motion at the right hand side, whereas larger substitutional impurity generates local stress at C. Okay, you can see the point C. Okay, local stress at point C and D that opposes direction motion to the right. Okay, right. So these are the lattice strain. Already we have seen this one. Okay, so this is how the lattice strain takes place around dislocations in terms of compression and tension. Okay, now coming to strengthening by solid solution alloying, small impurities tend to concentrate at dislocations region of compressive strains. You can see the figure A. Okay, partial cancellation of dislocation compressive strains and impurity atom tensile strains, right. Reduce the mobility of dislocation and increase the strength. Reduce the mobility. See, if this is the dislocation, when the dislocation is moving, okay, so this is larger in size, this is smaller in size, so this atom cannot move this atom. Okay, it cannot move this atom because it requires larger force. Okay, so in that case what will it do? It will start to overcome. Okay, at this time we have to apply more tensile stress. If you are applying more tensile stress, then this atom can climb or glide. Okay, can go upwards or downwards. Okay, thus making a barrier in the moment of dislocation. The strength of the material can be increased. Okay, either by means of interstitial solid solution or substitutional solid solution. This diagram illustrates how the barrier is formed with the help of substitutional solid solution atoms. Okay, the atoms of substitute atom, okay, which is lesser than size of the solvent atom, cannot able to move the bigger size atom, then it has to apply more strength, it has to release more energy. Okay, obviously the strength of the materials increases, right. Coming to the second one, okay, you can see the barrel distortion. Previously we have seen the pincushion and this one is a barrel distortion. Now you can see the atoms, okay, the atoms, solute atoms. Okay, major portion is solvent atom, this is a solute atom. Solute atoms are bigger in size. In this case, okay, so there the hindrance is caused by the smaller atoms. Either it has to move, the hindrance is hindrance, right. So the barrier, okay, if the barrier is there, then these atoms has to release lot of internal energy to move the dislocation, or these atoms, when these atoms want to move, okay, continuously, this acts as a barrier. If these atoms are the colored atoms move towards this side, then this acts as a barrier. So the strength of the material increases. Okay, right. So you can see the diagram, two diagrams which shows the tensile strength, effect of tensile and yield strength increases with the weight percentage of nickel. Okay, so you can see in the tensile strength along the y axis and weight percentage of nickel, that is concentration along the x axis. So you can see initially, right, the tensile strength is at 200. As the nickel concentration increases, you can see the tensile strength goes on increases. Okay, the concentration of the secondary element increases. You can see the tensile strength goes on increases until it reaches 400. Okay, at 50% of nickel, the strength, tensile strength is 4. That the meaning of this one, if the barrier is more, the strength of the material will increase. Similarly here you can see that is yield strength. Okay, first yield strength is considered at the plastic deformation stage. Okay, the tensile strength is the ultimate tensile strength. Okay, so the empirical relation, the equation governing the solid solution strengthening is sigma y is directly proportional to C power half, that is concentration or root C. Sigma y is directly proportional to root C or concentration. Okay, if the concentration increases, the yield strength increases. Okay, so the alloying increases sigma y and tensile strength. Okay, alloying is nothing but if you are adding more and more secondary elements, okay, then the strength of the material will get increased. This is what we can infer from the solid solution strengthening. Okay, this is the first type of strengthening mechanism. Now we will move on to the second strengthening mechanism called as strain hardening mechanism. Okay, strain hardening. What is strain hardening? Strain hardening is nothing but it is generally we call it as a work hardening, which takes place at plastic deformation. Okay, when a metal is subjected to tensile strength, tensile force, okay, up to its yield point, it obeys Hooke's law, that is stress is directly proportional to strain. So the equation governing the elastic limit is sigma is equal to E epsilon. Okay, where sigma is the stress and E is the Young's modulus, epsilon is the strain. Okay, or stress by strain is constant, that is E. Sigma by epsilon is equal to E, that is the equation governing the elastic region. If you go to the plastic region, okay, now materials starts to yield. Yield is nothing but permanently deform. Okay, at that time what happens? The material will starts to releases internal energy to oppose the external force. Okay, at that time, okay, the stress strain diagram starts to plunge downwards. Okay, because of the work hardening of the strain hardening of the material. Okay, due to that what happens? The material cannot dislocate further. Okay, in order to move the dislocation, we have to apply more amount of tensile strength. Okay, so until the internal energy is overcome by means of external energy, then the material once again loses its strength. Okay, then it will starts to deform until it reaches a ultimate point, ultimate tensile strength, after which it cannot hold the load and it starts to fracture. Okay, the common deformation, this strain hardening is mostly in cold working metals. Okay, mostly you can see this strain hardening will takes place in a cold working metals like forging, rolling, drawing and extrusion, right. So deformation at room temperature for most metals, common forming operation reduce the cross sectional area. Okay, so when the material is disturbed, okay, by means of a tensile strength, automatically it releases its internal energy to oppose its motion. Okay, right. So dislocation structures changes during cold working. You can see dislocation structure of titanium after cold working. The dislocation entangle with one another during cold work and dislocation motion becomes more difficult because they occupy together. Okay, these atoms join together and oppose the external force. Okay, so due to that what happens? The work hardening or strain hardening comes into picture. Okay, so dislocation density is nothing but the ratio between the total dislocation length to unit volume. Okay, so this is the property which governs strain hardening or work hardening strengthening mechanism. Okay, dislocation density plays a major role in work hardening. Okay, so for carefully grown single crystals, okay, you can see it is in the form of 10 power 3 millimeter power minus 2. Deforming sample increases density by 10 power 9 to 10 power 10 millimeter power minus 2, or heat treatment reduces the density to 10 power 5 to 10 power 6 mm power square. Okay, so as the yield strength increases, as the dislocation density increases. Okay, this is the governing equation. As the yield strength increases, the dislocation density increases. Right. So you can see the impact of the cold work. As the cold work is increased, yield strength increases. Obviously, the tensile strength also increases and the ductility decreases. Okay, ductility decreases. We know this property. Now our work is to improve the ductility also. For improving the ductility, we have to go for another secondary operations. Okay, you can see this is the diagram which illustrates between the stress and strain of a low carbon steel. Okay, with 0% cold work, 4% cold work and 24% cold work. Okay, so cold working increases the work hardening. Okay, you can see this is a 0% cold work, so you can see the strain is more, the ductility is more. Okay, now 4% of cold work. Now cold working means without heating the material is disturbed. Okay, now you can see it releases its internal energy to oppose the external forces, so that the ductility decreases. Okay, so you can see the strain is less. In 24% of cold work, you can see material becomes harder, okay, or stronger. Right, the strain decreases, the ductility decreases. This is how the cold work has an impact on the material strength. Okay, so the strain hardening exponent, this is the equation governing the plastic region. Sigma is equal to K epsilon power n. Already I told this equation. In the elastic region, sigma is equal to E epsilon, whereas in the plastic region, sigma is equal to K epsilon power n. Okay, where n is the strain hardening exponent and K is the strain hardening coefficient. Okay, or strength coefficient. Okay, so n value lies between 0 to 1. The higher n value, there will be higher strain hardening. Higher n value refers that higher strain hardening due to cold working. Okay, so this is the relationship between the sigma and epsilon with respect to true stress and true strain. Okay, a relationship between true stress and true strain, engineering stress and engineering strain, true stress and engineering stress. Okay, right. So effect of heat treating after cold working. So I told you the ductility gets decreases. Okay, so ductility decreases as the cold working increases. In order to improve the ductility, what we have to do is we have to go for heat treating, that is like annealing process. Okay, annealing. What is annealing? Heating the metal in a furnace above the upper recrystallization temperature, holding it for a longer period of time. Okay, in the furnace itself for the material to cool. Okay, this process called as annealing process. Okay, so during annealing, three process takes place: recovery, recrystallization and grain growth. Okay, so 1 hour treatment of annealing decreases the tensile strength and increases the ductility, that is percentage elongation. Okay, so 1 hour of treatment, that is annealing treatment, decreases the tensile strength and increases the percentage elongation. So this is the due to which the effect of the cold works are nullified. You can see this one. Okay, this is a graph which shows the relationship between the recovery, recrystallization, grain growth and effect of the material annealing temperature with respect to tensile strength, ductility. Okay, so you can see annealing, as the annealing temperature increases, okay, from 100, okay, 100, 200, 300, 400, 500, 600, you can see. Okay, so initially at 100 degrees centigrade the tensile strength is somewhere above 550. Okay, so now come to 600 degrees centigrade, annealing temperature to 600 degrees centigrade. See, you can see the tensile strength drastically decreases. Okay, between 300 to 400. Okay, and the ductility also gets increased. Okay, similarly you can see the ductility at this point. Okay, at 100 degrees centigrade, this 100 degrees centigrade. Okay, you can see the ductility is very less. Okay, now we are going for annealing treatment. If the annealing temperature increases, the ductility increases, the tensile strength decreases. Okay, so what is the 3 stages during heat treatment? Recovery. Recovery is nothing but okay, results from diffusion, that is extra half plane. You can see there is a recovery. Atoms diffuse to region of tension. Okay, so you can see this one how it is. So this is the dislocation. Now there is a barrier. Okay, now this is a barrier. So these atoms will, what is dislocation? Dislocation nothing but the start point of the plastic deformation. Okay, now once this plastic deformation starts, these atoms unite together to oppose the external agency to move the dislocation. Now see, the atoms comes together, diffuse to regions, okay, hindering their path. Okay, now, okay, so that the strength increases, the ductility decreases. Now dislocation annihilate during the what heat treatment, what happens? Dislocation annihilate and form a perfect atomic plane. Now after heat treatment, these atoms will expand and pave a way for these atoms to move, the dislocations to move. Okay, so you can see this one, this is how, okay, the obstacle dislocation, dislocation is obstacle, like this one. Okay, so you can see it is moving this one, this is obstacle. Okay, now it starts to come down in a new plane. Right. So 3 stages during heat treatment. In the first stage we have discussed about the recovery. Second stage, recrystallization. During the recrystallization stage, new grains are formed, have low dislocation density and smaller in size. Okay, and consume and replace the parent cold work grain. Okay, you can see this is the 33% cold worked brass. Okay, whereas new crystals nucleate after 3 seconds at 580 degree centigrade. You can see new crystals will be formed here. Okay, you can see new crystals will be formed. Okay, initially the grain structure is bigger in size. Now the grain structure somewhat starts to decrease. Okay, so as the recrystallization continues, all cold work grains are eventually consumed and replaced. See, the cold work grains are consumed. Now it will disappear and you can see the uniform grains structure. Okay, after 8 seconds. Right. So next stage is grain growth. Okay, now after the homogeneity is attained, then the grain starts to grow at longer time and average grain size increases. Smaller grains shrink and ultimately disappear. So larger grains continue to grow, so that the material now it has a very good structure. Okay, so see, the unit cells are formed on their places and the grain boundaries are formed. Okay, so the empirical relationship for this one is d power n minus d naught power n is equal to k power t. Okay, kt. Okay, so this is the graph which illustrates the effect of the annealing temperature with respect to tensile strength and ductility. Already we have seen this diagram in the previous slides. Now you can see the grain size, how the grain size, see this green color in the beginning, it's a recovery stage due to cold working. Cold working means, like for example, if you are passing it through 2 dyes, okay, 2 dyes, okay, forming process, okay, wire drawing or deep drawing process. Okay, right. Now recrystallization, new grains are formed. Okay, then once again the grain starts to grow. So effect of recrystallization temperature. Okay, the temperature, recrystallization temperature is the temperature at which the recrystallization just reaches completion in 1 hour. Okay, you can see the recrystallization temperature is between 30% of melting point and between 60% of its melting point. Okay, so it should be carried out in between 30% of melting point and 60% of melting point. For a specific metal and alloy, the recrystallization temperature depends on percentage cold work, that is recrystallization temperature decreases with increasing percentage of cold working. So purity of metal, pure metal, for pure metal the recrystallization temperature decreases with increasing purity. Okay, so if a metallic grain growth is assumed to occur as a result of surface energy consideration and the diffusion of atoms across a grain boundary occur, then it is expected that at any given constant temperature a grain growth law given below is followed, that is d power 1 by n minus d naught power 1 by n is equal to kt, where d is the final average grain size diameter and d naught is the initial average grain size diameter, n is the grain boundary exponent and t is the time and k is the constant. N is less than 0.5 and tend to increase with the time and approach 0.5. Okay, so with this we will stop our discussion now. Okay, thank you for your attention.